Imagine a world where AI doesn't just predict the next word, but understands the structure of thought itself. Where models don't just mimic language, but grasp the logic, causality, and even the intent behind it. This isn't science fiction. It's the frontier of modern AI, reasoning at scale. For years, large language models have dazzled us with their ability to generate human-like text. They write essays, draft code, even explain quantum physics. But here's the catch: they're often just pattern matchers. They don't think. They don't reason. They predict the next token based on statistical likelihood, not causal understanding. That's why the real breakthrough isn't in size. It's in structure. And the latest research points to a radical shift: reasoning as a process, not a byproduct. Let's break this down. At the heart of every LLM is the transformer architecture, layers of attention mechanisms that weigh the importance of different words in a sentence. But attention alone isn't reasoning. It's pattern recognition on steroids. So how do we teach a model to think? The answer lies in chain-of-thought prompting. Instead of asking a model, what's 27 times 19, and getting back 513, we say, let's solve this step by step. And suddenly the model starts to show its work. 27 times 10 is 270. 27 times 9 is 243. Add them, 270 plus 243 equals 513. This isn't magic. It's a shift in instruction. By forcing the model to articulate intermediate steps, we're effectively simulating a reasoning pipeline. But here's where it gets deeper. Chain of thought isn't just a trick, it's a signal of latent reasoning capability. Models trained on massive amounts of text develop this ability naturally, but only when prompted correctly. And researchers have now found a way to amplify it. Enter self-consistency and tree-of-thought reasoning. Self-consistency means generating multiple reasoning paths and choosing the most frequent answer. It's like having a team of AI thinkers debate the solution and voting on the best one. This dramatically improves accuracy, especially in complex math or logic problems. Tree-of-thought takes it further. Instead of a single linear path, the model explores multiple branches of reasoning, like a tree. At each node, it evaluates whether a path is promising. If it hits a dead end, it backtracks. This mimics human problem-solving, trial, error, and refinement. But even these methods are limited by the model's internal knowledge. They're still constrained by what's in the weights, what it was trained on. So the next leap: external reasoning tools. Imagine an AI that doesn't just generate text. It executes code, queries databases, runs simulations, and verifies its own logic. This is where agent-based architectures come in. Think of it like this: the LLM is the brain. But it's connected to tools, code interpreters, calculators, search engines, symbolic reasoning engines. When faced with a complex problem, the model doesn't just guess. It plans, decomposes, executes, and evaluates. For example, calculate the trajectory of a projectile launched at 45 degrees with 100 ms initial velocity. A traditional model might hallucinate an answer. But an agent would break this down. First, extract physics equations. Then, compute horizontal and vertical components. Then, simulate the motion over time using a numerical solver. Finally, return the range. And it does it by generating and running code in a sandboxed environment. This is no longer just language modeling. This is embodied reasoning, where the model interacts with the world through tools. But here's the most profound shift: reasoning as a learnable process. Researchers are now training models not just to produce answers, but to optimize their reasoning paths. Using reinforcement learning, models are rewarded not just for correct answers, but for efficient, logical, and explainable reasoning. One study trained a model to solve math problems by minimizing the number of steps and maximizing consistency. The result: it didn't just get better at math, it developed a kind of metacognition. It learned how to think better. And this brings us to the final frontier: generalized reasoning. We're moving beyond domain-specific tricks. The goal is a single model that can reason across math, physics, programming, ethics, and even abstract philosophy, using the same core architecture, the same reasoning engine. This isn't about memorizing facts. It's about understanding principles, like causality, conservation laws, logical inference. Models that can not only answer why, but also justify their answers with clear, traceable logic. But let's be clear, we're not there yet. Current systems still struggle with long chains of reasoning, self-consistency under uncertainty, and handling contradictions. They can be brittle. They can hallucinate mid-reasoning. They can get stuck in loops. Yet the trajectory is undeniable. The tools are maturing. The architectures are evolving. The data is growing. And the implications: they're transformative. In science, AI agents could simulate complex experiments, propose hypotheses, and design new research. In education, they could tutor students not by giving answers, but by guiding them through reasoning steps. In software development, they could write, debug, and verify code autonomously. This isn't about replacing human intelligence. It's about augmenting it, giving us tools that don't just respond, but think. So the next time you ask an AI a question, remember, the real magic isn't in the answer. It's in the path it takes to get there. Because in the age of reasoning AI, the journey is the intelligence. The future isn't just smarter machines. It's machines that understand, that reason, That's think. And that's not just the next step in AI. It's the next evolution of intelligence itself.